Today we will see regarding the MapReduce jobs, and this is again a theoretical topic wherein we are going to understand what do we mean by MapReduce job, and also we are going to see that given a problem statement, how to think in terms of key value pairs, or how to think to solve the problems in a MapReduce paradigm. So to solve a problem in the MapReduce model, it's entirely a different way of thinking the thinking it's entirely different way of thinking the problem to solve it. Okay, so which means that it will not be a traditional way of solving the problem, but we have to see that how the map tasks will be executed, what all things goes in the map tasks, and then what is that map task will emit that will go to the reduce task, and reduce task how it will, what thing needs to go, what all things need to go into reduce task to generate the final output. So when you talk about a MapReduce job, so a MapReduce job is decomposed into tasks. It is decomposed into tasks, and there are two kinds of tasks. One is a map tasks, and there's a reduce task. So in a MapReduce job, you have only two kinds of tasks: map tasks and reduce tasks. And these are the two design principles, and this is how it is designed. I mean, these are the two design principles. So when you talk about a MapReduce job always starts with a map task and it ends with reduce task. Or I can say it ends with zero or more reduced task. That is also fine. But here you can ask a question: can we have zero map task?
Yeah.
No, you cannot have a zero map task. Okay, if there are no map task, that means nothing is running. So because I have
Okay.
just told you, a MapReduce job always starts with a map task. It should have more than one map task. Okay, it should have at least minimum of one map task. If you have a zero map task, that means the MapReduce job is not running at all. So a MapReduce job always starts with the map task and ends with zero or more reduced tasks. The second thing which you need to understand is the reduced task will never ever start until all the map tasks are finished. Okay, once all the map tasks are finished, the output of the map tasks will be transferred to the reduced task, and then the reduced task will do something and generate the final output.
Okay.
Now, to just understand in a more in a more little bit of a detail, like because you know that when you talk about a file or data, MapReduce job works on a data, but in with respect to HDFS, the data is the thing, but it's in the form of a blocks: B1, B2, some 100 blocks. So each of the block is processed by a map task. Then the map task will generate some intermediate output. That intermediate output will be taken by reduce task and it will generate a final output. Okay,
Okay.
that's one thing. Now again, a little bit more diagrammatically, let's understand. So you have a sample file. Let's say it has been broken into two blocks, B1 and B2. B1 is stored with machine 0, B2 is stored with machine 1. Let's say assume that it's a replication factor and this is the metadata information stored by the name node. I'm not interested in that. What I'm interested right now here is you have these two blocks in these two machines. B1 is machine 0, B1 is machine 0, B2 is machine 1, and this is another data node machines. So I have three slave machines. So there are two blocks of data and that will be taken up by, so the two blocks of data will be processed by two map tasks. Okay, and also let us
Yeah.
assume that the framework has decided to run the map task on the above two machines and the reducer task on the below two machines. Just an assumption right now.
Okay.
So the two blocks will be taken up by the two map tasks. These map tasks will process the data and that will generate some, let's say, output 1, and this has generated output 2. That output 1 and output 2 goes to the reducer machine and that is processed. So reduce task will process output 1 and output 2 and will generate the final output. Again, we are talking about a very high level. Okay, from 100 feet we are seeing this, how this is happening. Okay. Now,
Yeah.
the interesting thing, let us answer this question to understand that whether whatever we have learned till now, whether it is applicable in the MapReduce job or not. Now, don't you think the map task always needs to be run on a machine data is present? Of course, right? It has to
Yeah.
run because map task always needs to run on the machine data. Ideally, all the map tasks should run on the machine data is present. That concept which we have learned long back, which is known as data
That,
localization.
that I know.
Data localization basically means localizing the data or running the application on the machine where data is present. Or in other words, where we have understood our introduction module, data localization means that don't move the data at all. Instead of that, run the application on the machine data is present. So here we are not moving the data, but we are executing our tasks on the machine data is present. So we are trying to achieve the data localization. Ideally, we should be running the map task on the machine data is present because MapReduce job always starts with the map task, right? So I
Yeah.
first need to process the data. That's why the map task ideally has to run the machine data is present. Okay, and let us answer the second question. Hello, can you hear me?
Yes, yes, I'm listening to you.
Okay, I think my some
Uh, I have a question. This data localization, is it applicable for the reduce phase as well, or it's only for the map?
you need to understand and tell me that do you think the data localization concept is it applicable
Yeah.
for this task or not? This question is asked here. Do you really think the data
Yeah.
localization concept is applicable to this task? What do you say?
Yeah. Actually, I'm not sure whether the output generator is it going to be saved somewhere or is it going to be in the memory? I mean the RAM.
So it will be said the which output you're talking about, the map task output.
Reduce task. Map I understood. Yeah. Map anyway. Data localization will be applicable. Program will be running
But
on
the
the data
output, if
node.
you have
Where
just
the block?
observed, if you have
Yeah.
observed the output of the map tasks, output 1 and output 2, it is going to be transferred across the network and is going to the machine register task is running. So wherever there's a data transfer, that means the register task is running on this machine, right? The register task is running on this
Yeah.
machine, and the data is coming to the
Okay.
register machine, or the machine where the register task is running. So whenever there's a data
Okay.
transfer, then there is no data
Localization.
localization. Okay, so register task is running here, and the data is coming to the machine. That data is coming to the application or task. That means there is no data localization concept applicable to register task. You can always
Okay.
argue you have taken a different machine. That's why you are saying that. You can all the register task can run on this machine also. But in that
Okay.
case also, the output from this machine has to be transferred across the network. So again, the data
Oh
transfer
yes.
is happening. So reducer task. So the data localization concept is not applicable for the reducer task. Okay, just let me just quickly go to. Now we will talk about in this model. Just now we have seen the high level definition of MapReduce, or what do we mean MapReduce job at a very high level. Now we are going to little bit drill down. Now we are going to drill down actually into the internals of our MapReduce concepts. So right now, so we have already seen couple of definitions. So a MapReduce or a MapReduce is basically it's a framework, and what kind of framework it is? We are talking about it's a computation framework, right? Now
Yeah.
MapReduce or a YARN is a computation framework which is used for processing the data residing on the HDFS. And how does the data resides on the HDFS? In the form of blocks.
Yeah.
And just now you have seen, right, how the map tasks and the output goes to the machine. Now, when you talk about a MapReduce job, it consists typically of 5 phases: map, phase, partitioning, sort, shuffling, reduce. Sort and shuffle, sometimes they are combinedly together, they name as sort and shuffle phase. It's okay to say there is a sorting phase and the shuffle phase, or it is okay also to say you merge this and you say sort and shuffle phase, one and the same thing. Don't have to worry about that. But right now, I'm not. Right now, let us not worry about any of those intermediate phases. Right now, it is sufficient to understand that a MapReduce job starts with a map task and ends with reduce task. Okay.
Yep.
Uh, and now a single map task works typically on one block of data. And this is the default nature, that a number of map tasks equal number of block the dataset has. Now, the default nature of a MapReduce job is, if you let's say, on a particular data set, if you're running, on a particular data set, if you have a data on HDFS, and let's say it has a 3 blocks, and so if you run a MapReduce job on this, in the default, by default, number of map tasks equal to number of blocks. And default number of reduced task is 1. That's a default nature.
Okay.
So how many number of map tasks it will run in this case? If you have on this data set, since there are 3 blocks, it will be 3 map tasks
3.
and 1 reduced task. That's a default nature. Okay. But here the statement says that a single map task works typically on a one block of data. Now, the word typically, to understand the word typically, let us go back again what I have just explained you. Assuming the block size is 128 MB.
Yeah.
Assuming the block size is 128 MB. Now, this particular data has a 3 blocks, or I can say this data has a 3 128 MB blocks, right?
Yep.
Okay, so by default, each map task processes a block of data. In this example, each map task is going to process how much amount of byte of data? 120 MB byte of data, right?
Yes.
Yes. The word
Yes.
typically
Yes.
means that you have the flexibility. You have the flexibility to change the amount of data that each map task is going to process. We are going to understand that
Okay.
later, but right now just it is sufficient to understand the word typically means that the amount of data that each map task is going to process can be changed, and you can change the number of map tasks. That is what the word typically means. By default, number of map tasks equal to number of blocks, or in other words, I have taken an example that assuming the block size is 120 MB, so for this data set you have a 3 120 MB blocks, so each map task is going to process 120 MB of data. The word typically means that you can change this default nature. You can say that I don't want my map task to process 120 MB of data, but instead of that, I want each of my map tasks to process 64 MB of data, or 32 MB of data, or 256 MB of data, or 1 GB of data, or something like that. Whatever number, you can say that. The word typically actually means that. We'll talk in detail later. Now,
Okay.
after all the map tasks are completed, the output from the map is passed on to the machine the reducer task will run. That's what we have known, right? So the map tasks,
Yep.
so the reducer works on the mapper output. The point which you need to understand, the reducer task or reduce task works on the mapper output. Okay, and here that's what just a little bit of more explanation. Assuming that this is your file, which is of size 120 MB, the block size is 64 MB, the replication factor 3.
Yeah.
So how many blocks the file will be broken into? So you know that it will be broken 2 blocks and replication factor 3, so 3 replicas, and the replicas are
Yeah.
distributed across several machines. And keeping in mind, no two same replicas will ever result on the same machine. So I have just again taken the same example. You have B1, 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 B2, B2, B2 in these machines. This is distributed like this. and you have another slave machine, which I actually, that why I have given here, why I have taken this machine here to just to showcase that the mapper task output will be transferred across the network and will be going to the register machine. So this empty space is the network. Now, how many number of blocks you have? Two. You
Three.
don't have to.
Two.
You'll not run your task on the replicas, right? It's redundant.
Yeah.
So you ideally have a two blocks. So number of map tasks will be equal to two. Okay. And please also
Yeah.
understand that each of the map task is running on a separate JVM. Each of the map tasks which will be running now, they will take two blocks of data. You don't know which all blocks, but assuming this, the map task, one of the map tasks take this block of data, and the map task take this another block of data. And please
Okay.
understand that each of the map tasks which is running, it is running on its own JVM, and hence they are independent tasks. And what do we mean by independent tasks? Independent tasks means that failure of one task will not affect the execution of other tasks.
Okay.
Failure of one task doesn't affect execution of other tasks. Also, you need to understand that it is does not make sense to run these map tasks on your node manager, or you can say or application masters JVM. Right? It does not make sense to run on any of the processes JVM. The reason is these map tasks logic will be written by the developer, and if that map task has some bug, then it throws an exception, so entire JVM brings down, entire JVM will come down. And it does not really make sense that the processes goes down unnecessarily because of the inability of the developer to write a proper code. So that's why these tasks, whatever the map and view stuff, they run on a separate JVM. And as soon as you say they run on a separate JVM, these are independent tasks. The word independent, you should understand that failure of one task, if this task has failed, it will not affect the execution of these tasks. Okay. Now coming back here, whatever we are trying to understand here, that number of blocks are two, so the number of map tasks will be equal to two. And these two tasks will run parallelly, and each task is processing different block of data. And once the map task is completed, the output will be transferred over the network where the user task is running. So I've just taken, so this output of this map task is output 1, this is output 2. They will transfer over the network. Again, to emphasize the fact that the data localization concept is not applicable for the reducer tasks. And a reducer task will work on the outputs of the mapper task, and it generate the final output. Now let us talk about the terminologies. MapReduce job. So what do we mean by job? A job, we define it as a complete execution of a mapper and reducer tasks over the entire data set. And I think we have already known that Hadoop, the MapReduce job, is a batch mode.
Yeah.
And what do we mean by batch mode? Batch mode means that even though the data is partitioned into smaller blocks, you don't have the flexibility to access and analyze the individual block. You have to process all the blocks of data at any given point of time. That is known as a batch mode. So, if you are not aware of this concept, please visit my previous recording. Yeah. So, MapReduce job is also known as a batch mode. Okay, I have written it here. Yeah. Now, what is a task? A task is a single unit of execution. And just now we have seen that there are two kinds of tasks. One is a map task, another is a reduce task. The map task works typically on a block of data. The word typically, again, I have just explained at a high level, but you should understand that by default, number of map tasks equal to number of blocks. That's a default nature. The word typically, as I've explained you at a high level again, that it means that you can change the amount of data that each map task is going to process, which will change the number of map tasks. And reducer task works on the mapper output. Now let us talk about the task attempt. Now, task attempt, the name itself says that the task the attempt will be done by the task. Now, if you take an example of a student who is going to give an examination, right? So at that time, his status, his mind status, is not to score 100 out of 100, right? What he says, what he thinks, that I want to score 35 first. What he does actually, he first makes an attempt to clear the paper. Everyone's mindset when they enter into the examination center is that they make an attempt to clear the paper. And sometimes even the topper can fail the examination because if the question paper is out of syllabus, or he has not prepared well, or for some other reason the topper also can fail in examination. When I say topper, I basically mean a very new brand machine which is
Okay.
executing the task can fail because of some other reason. Now, if you want to apply this logic to your college, in your college examination, right? So you have a 5 papers, and let's say one of the papers, electronic devices. It's a very tough paper in, let's say, in the third semester, and for that, so you attempt that paper and you fail for some reasons. Maybe the questions were out of syllabus or stuff or whatever reason. Okay, so your university guy, the university people, they know that this guy might not have studied all the year. So what they do, they give one more attempt. So you have failed in the mains examination. Now you got one more attempt to clear the paper, which is supplementary. Again, you get one more attempt to clear the paper. Let's say if in supplementary also, if you fail to pass, then again you got another attempt. So let's say there are 4 attempts to clear the paper. So what happens if you exhaust the number of attempts to clear the paper? What happens? Instead of, irrespective of how many papers you have cleared in that examination, does not matter. You have failed that examination, you have failed that particular paper, electronic devices, so you will get an year back. That's the same. So you have understood the logic, right? And now it's the same situation happens here. Let us, so now hang on with me. Now let us see that. How does it happen? How does it, the same example applies over here? Now you have here, assuming your data set has been broken into 2 blocks, and you can very well see there are 3 replicas, right? But
Yes.
ideally, you will not run your task on all the replicas. It's a redundant. So what you will do, you will run only on unique number of blocks, or you can say that, right? Number of blocks is 2, so number of map tasks is 2. Okay, tasks are running independently, and each task is running independently, or you can say that both of the tasks are running a separate JVM. Okay, now you can consider, okay, that's fine. Now one of the tasks is completed, so you can think this paper is your mathematics, which is easier, and it has been completed, and this is electronic devices, and it is running, and it has failed for some reason, and the task can be failed because of network failure or machine failure. So basically, the first attempt, it has failed on this machine. Then the second reattempt will be done on the same machine. Okay, second reattempt is being done, and again it has failed. The third reattempt will be done. Again, it has failed. Now, what does the framework see? That uh, this machine might be a problem. So all the tasks are failing on this machine. So this machine might be a problem. At this point, if you are running a multi-node Hadoop setup, then what the framework will do is to schedule this task on some other machine, on this replica. So it might choose some other machine, and that's your final attempt. I mean, default number of attempts are 4, and if this attempt also failed, then the irrespective of how many tasks has been completed successfully, does not matter.
Okay.
So if any task by default 4 times, by default fails by default 4 times successfully, then entire job fails and no output is generated.
Okay.
So what I'm trying to,
So my
yeah,
yeah.
just 1 minute.
Just a
What I'm
question.
trying to say,
Uh,
that you have just 1 minute. I have 100 tasks, and out of this 100 tasks, 99 tasks are successfully completed, and one task has failed 4 times successfully, that is one after the other continuously, it has failed 4 times, then does not matter. Your entire job fails and no output is generated. But you also have the flexibility. But in the map, just I want to tell you that that's a default nature. But you also have the flexibility to tolerate the failures. You can say that if my MapReduce job has passed 72% or 75% percentage, or you say that I can tolerate up to 30% of my map tasks failure. So if there are failures happening, but you have set this property, then you will still get the output. Then it will get the output. Okay, you have the flexibility to say that if my job has completed 73% successfully, then give me the output. Yes, Ajit, not only.
Yeah. So the query is that the reattempt will be always on the same data node in case any of the task fails, or after one or two attempts
That's
it
how
will try
that's how
to.
it has been designed. It tries to attempt on the same machine.
Okay.
Yeah.
So it will never try to run it on some other data node
It
where
might,
same
it
block
might, it
information
might.
have been.
That behavior is undefined. I have not seen the actual that you cannot say that it will not be attempted. It might be
Okay.
happen that it can run on the it can, but ideally it runs on the same machine which I have seen. But I'm not sure. I cannot tell you 100% that if a task fails, it will directly reattempt on some other machine. I cannot tell you by 100%. But what I have seen is it always executes on the same machine.
Okay. Yeah.
Yeah.
Thanks. So.
Yeah. Now, speculative execution. Let us talk about speculative execution. And now, speculation, basically, the literal English word means anticipation, or other word, imagination. Okay. To understand this, let's say I will take again an example that uh, you know the Silk Board, right? There's a Madiwala market.
Yeah. Yeah.
Now, in the market, in that Madiwala market, and I am at Marathalli. Okay. You are in Electronic City, and this guy is also in Marathalli. Let's say Vipin is also in Marathalli. Now, what I have in the market, I want to buy a 10 kg of sugar. In the market, there's a shop wherein I have to buy a 10 kg of sugar. What I say, what I order this guy, Vipin, boss, go and bring my 10 kg of sugar from that particular shop and that from that market. So what he does, he takes up a bus, starts from Marathalli, and then starts right, and then starts going towards that market. So you know that you have a lot of obstacles, Kadabisnalli, Sarjapur, blah blah blah, and what I see and what I feel that and what's happening right now is that at every 5 or 6 seconds, or let's say for every small duration of time, this guy is calling me and telling me that I am at this junction, I am at this junction, I'm at this junction. So he's saying that I am at this
Okay.
Marathalli junction. I am not being moved. I am in this Marathalli. I am at this Marathalli. So he says me 3 or 4 times that he is at the same location. What I think, then boss, this guy is slow. What I will do
Okay.
is Sajid, whether let me ask Sajid to bring the 10 kg of sugar. And now you also start from the beginning.
Okay. Yeah.
What I have thought of that this Sajid might be a faster because he might know some shortcuts. He might have some bike. He might be having some or the other thing that he can be a faster guy. That's what I will think. No other rocket science logic. Okay, I will just imagine that
Okay.
this guy could be a faster machine. Now both of them started. Now both of them are running, and now Sajid goes and calls me back that boss, I got you 10 kg of sugar. What will I do with Vipin? I will say, Vipin, come back. And now the
Okay.
same concept is applicable here when the few tasks are running slow. So if you remember in the introduction module, I have introduced the term speculative execution. At that time, I have given a scenario like the strength of the chain is determined by the weakest link. Now, similarly,
Yes.
if a MapReduce job has spawned 100 tasks, and just now you have seen that each task runs independently. So 99 tasks has taken 1 second to complete. I'm just taking a small assumption. And one task, the 100th task has taken 1 hour to complete the job. Right? This is a slow running task because it has taken 1 hour. So you don't say your efficiency of the job is 1 second, but you say it's a 1 hour. So the efficiency of the job is determined by the slowest running task. How can you
Okay.
improve this performance? How can you improve the performance of a slow running job when the few tasks are running slow? So the concept is known as speculative execution. So the point here is speculative execution is the concept of improving. So speculative execution is a concept of improving the performance of a job when few tasks are running slow. Okay. Now let us talk about speculative execution diagrammatically. Now here you have two blocks which will be taken up by two map tasks, which we have already seen now. Two blocks, two map tasks. Each map task is running. Let us assume that this task is completed, but this task is running. Okay. And now here, let us the task tracker I have given, but you can always think as a node manager. So this task tracker is sending 10% signal, 10% sorry signal. I'm very sorry, 10% progress report. And again, after some time, because you understand that the slave process will send the heartbeat signal to the master process. So node manager will always send the or in this case application master always tries to convene, always sends the heartbeat signal to the node manager. Now let us not go into the details. So what I'm trying to say, it's sending the same heartbeat signal, it's sending the same progress report. Every heartbeat signal, it is sending the same progress report. So the framework waits for 3 to 4 heartbeat signals. So if it has received the same progress report for 3 to 4 heartbeat signals, then it assumes the task is running slow. And in that case, what will happen? It will again start the task. So the same B1 block of data, right? I've explained you Sajjit and Vipin's that particular same scenario. So this task is running. The framework will run the task on some other machine on the replica, and these two tasks are running parallelly. So this is known as speculative execution. So running a redundant tasks parallelly to improve the performance of a slow running task. So the two tasks are running parallelly on the same block of data. And this is redundant because this task is running slow. That's why we are running it here, so that we are assuming or speculating that this machine could be a faster machine. Now, if any of the machines finishes first, so this let's us assume that this task has finished first. So this will be completed and this will be marked as a kill.
Okay.
Okay. So
Yes.
just now I introduced two kinds of tasks. One is a failed task and is a killed task. Failed task and a killed task. Right now, so failed tasks are those tasks which will be real. The difference I'm trying to explain you. The failed tasks are failing due to exceptions like machine failures, network failure, whatever reasons. But these failed tasks will be reattempted, and that will
Okay.
be by default 4 times. By default 4 times, and you can configure these attempts by these two properties. For the map attempts, you can configure mapred.map.max.attempts, and for the reducer, you can always mapred.reduce.max.attempts. Okay. Killed tasks are those tasks which are run as a part of speculative execution. So these tasks will specifically run for this speculative execution. So you should be understanding the difference between the failed task and the killed task. Killed tasks are never reattempted; they run as a part of the speculative execution. Failed tasks, they will be reattempted by default 4 times.
Yes.
Okay, and now let us talk about input split. Now, input split, as I've explained you in a couple of slides back, that the number of map tasks equal to number of blocks. Also, I have introduced the word typically, wherein I have referred that a map task typically works on a block of data. So the word typically we are going to understand now, wherein I have understand a couple of minutes back that the word typically means that you have the flexibility to change the amount of data that each map task is going to process. The default nature is that each map task processes a block of data, but you can always have the flexibility to change the amount of data that each map task is going to process. Now let us talk about that. So as we have already seen, the number of map tasks equal to the number of blocks, right? Now input split is
Yeah.
nothing but a portion or a chunk of data. The data is nothing but a block right now. You understand that when I say data, I'm explicitly referring to a block, because on HDFS the data is stored in the form of blocks. So a sample file has been broken into, let's say, 3 blocks. So I'm talking about one of the blocks. A portion or a chunk of data on which the map task will operate. Input split is just a reference to the data. Now, whenever you say it's a reference, you remember that reference is always referred to the memory location. So if anyone has given you a reference from 0 to 64 MB in memory, then you can spawn either entire 64 MB, or you can spawn either 32 MB or 16 MB or whatever. Okay. Now the correct statement, which I would want you to always say is number of map tasks equal to number of input splits, not number of map tasks as number of blocks. So you should always say the number of map tasks is equal to number of input splits. Okay. Now, how do I define the number of input splits? It is determined by the input split size. So whatever input split size you have defined, that number of input splits will be determined, and then hence it will determine the number of map tasks. Is there any default value of the input split size? Yes. The default value of the input split size is the block size, whatever you define. For example, the block size defined as a 64 MB, then the default value of the input split size is equal to 64 MB. Okay, so by changing the input split size, the number of input splits will be changed, and hence you will see the number of map tasks will also change.
So,
Yeah.
yeah. Hi, Shom. Sorry, I was not here. This is regarding the input split. What I was told, or what I'm aware of, the cases where number of input splits is different from the block is when see, typically one block may not complete because map works on a complete record. So in case one record spills to the next block, is that the case? Why we have different
No, no, no. That
input
is a different.
splits?
That is a different. You are
That's
mixing
a
the
different.
concept. You are mixing the concept of a record reader. The record reader will go to the next input split and bring the broken word. That is a different thing.
Okay, okay, okay.
Yeah.
Thanks so much because I was maybe wrongly given the information. I thought input split is the case, and the record splits to the next block.
No, 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 no. That's different concept. No, 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 no. That's not. That's a different thing. Yeah. Now
Okay,
here your file size is 120 MB. Your block size is 64 MB. Replication factor 1. So how many blocks it will be broken into? It will be broken into file size 2 blocks. B1, B2, replication factor 1. Okay. And okay. So how many input splits are there? So the case 1. So my case 1 is this, wherein I am saying the case 1, it says that the input split size is equal to block size, which is equal to 64 MB. My question is, how many input splits you see? 2, right?
Yeah.
You see 2 input splits. Yeah. So the number of map tasks will be equal to 2. And that's a default nature, no? We have seen that number of map tasks equal to number of blocks. And input split size is your also equal to the block size, so you will have number of map tasks as 2.
Yeah.
Now, each map task is going to process how much amount of data this time? 60. I mean, in this case, 64 MB of data. and to understand it diagrammatically. So you have a 64 MB of data, and each map task is going to process 64 MB of data. That's a case 1. Is this clear? Now, the second case. Please understand, I'm not going to change the block size, okay? The block size remains the same. But now the input split size I'm changing. This is my case 2. Now, can you tell me how many input splits now in this case?
4.
You will have 4 input splits. And hence the number of map tasks equal to 4. And each map task is going to process 32 MB of data. So that's 64 MB of block of data. So one of the map tasks will take 32 MB, another map task 32 MB, 32 MB, 32 MB. So 4 map tasks will be running. That's your case 2. Without changing the block size. Now case 3 is that your input split size is 120 MB. I can take it as a 256 MB also. Please understand, it's a file size is 120 MB, but I'm talking about an input split size which is greater than equal to your actual file size. Now in this case, how many input splits? 1? Yes or no?
Yes.
And hence the number of map tasks is equal to 1, or each map task is going to process 120 MB of data. Correct. I mean to say whatever the input splits I have defined. Now this is a scenario, but do you think you have a 120 MB blocks or 120 MB chunks, whatever? No, you don't have it, right? 64 MB is in one machine, 64 MB is another machine. So what is going to happen is you are going to transfer this block of data, and then it will make 120 MB, and single map task is going to run. This is a very typical case, right? If you see that this is, if you want to reframe this particular case wherein I am processing all the blocks of data by single map task. So if you read this statement, this particular case is a typical case. Irrespective of how many blocks the file has been broken into, ideally we are not processing them in a distributed or parallel fashion. What we are saying that bring up all these blocks of data into one machine, and by a single map task process it by using a single or use a single map task to process it. Irrespective of how many blocks the file has been broken into, all the blocks of data is to process single map task. If I am reframing this particular scenario, if I want to reframe, I can also say that it is like a single standalone Java application processing the entire data, and this is typically useful in the image processing and face recognition. And also, please here, I have just shown you that data gets transferred, right? I can mitigate that transfer of the data if I have a replica. Correct. If I have already the replica in this machine, then I would have mitigated the transfer of the data. So replica plays a very major important role. Okay, is this clear, guys?
Yeah, so again, I have a question here. How this replica should be on the same machine, right? Then only we can avoid this data transfer.
Yes.
But again, earlier you said like we cannot store 2 replicas on the same machine, right?
But 2 different replicas. No, I'm not
Oh,
talking
okay,
about
good.
V1. We're talking about
Yeah,
V1, V2.
yeah. Okay, good. No, yes, yeah, you're right.
Yeah.
Thank
So
you.
Hello, Som. Actually, it's a bit too confusing in which inputs split size is greater than the file size. If you don't mind, can you explain one more time, if you don't mind?
So this particular scenario is using the face recognition. Now let us assume that in patient's images, when you take up, let's say, a cancer patient image or any other image, I'm talking about specifically the face, because a patient who is talking about a patient who is been eating gutka, pan masala, and all, he actually gets an oral cancer. So the oral cancer generally starts with your neck or starts with the jaw and goes till the neck. It is affected like this. It starts from the jaw. Okay. And now we want to analyze this data. So what you do, it's a very big image, assuming it's a 120 MB image. And what you do, you break it, because HDFS does not know, or when you put the data on the HDFS does not know whether it's an image or whatever. So you put this data onto HDFS, and what happens here, you know that the data gets broken, replicated, and distributed across several machine, assuming the data has been broken like this. So you have two machines, and some part of image came up here, and other part of the image came up here, which has a cancer portion, to give this idea. So here some part of the cancer is there, here some part of the cancer is there, here also some part of the cancer, right? Now when you do this exercise, if you really want to find out that how much of a cancer has been really been affected to this person, then you need a pixel by pixel, pixel by pixel, pixel by pixel information to do that activity, right? So you cannot do this in a distributed fashion, because just now you have understood that these two map tasks runs on a separate JVM. There is no interaction between these two map tasks, and you ideally should not have any kind of ideally you should not have any such scenarios wherein you wanted some information from other block of data. The programs or the logic or whatever the processing you should be doing, you should be done in an independent fashion, so that you should, whenever you're processing this, you should not require any of this information. But this is a scenario wherein you might want to do some kind of a synchronization between these two map tasks. If you really want to see, if you're processing this pixel, you might want to know what is the value of this pixel here. So that's why in this scenario, what you do is you ideally bring up these. What you will do, you will bring up the entire face onto one machine, or entire image onto one machine, and then process as a whole. So the entire data to one machine. That is the use case. How do I bring it up? Is by changing the input split size, or by setting the input split size to a value greater than the actual file size. And when you put that, then what will happen? The framework will bring the entire data to one single machine and then process it. Is this conceptually clear now?
Yes, so
So that's what you do here. You put your block size greater than the file size, so that your all the blocks of data comes to one machine. So this is what you do. And how do you do that actually? So it uses this formula. Input split size is the maximum of a minimum split size, comma minimum of a maximum split size, comma block size. So it is governed by three properties. It is controlled by three properties. You have this property, MapRed.min.split.size, the default value being the 1 byte. MapRed.max.split.size, the default value being 2 raised to the 63 minus 1. And this is anyways, it is dfs.block.size, it is per file. So block size is per file, right? Correct. So now if you see input split size, what will be the input split size if I take the default values? Minimum split size is 1 byte, comma minimum of maximum split size is 2 raised to the power 63, comma block size is 64 MB. Maximum of 1 byte, the minimum would be 64 MB, and the maximum would be 64 MB. So you can see that the minimum splits, the input split, the default value of the input split size is the block size. So by default, if you don't change anything, the number of map tasks will be equal to the number of blocks. Now coming back to this case, how do I? So here your block size is 64 MB. Here your block size is 64 MB. So I'm at case 2 and my block size is 64 MB. So my left hand side is 32 MB And what should be the values of the minimum, what should be the value of minimum split size and the maximum split size, so that the left hand side and the right hand side are equal for this particular case. So maximum of, I can put as a 1 byte here, comma, minimum of, I can put as a 32 MB, 64 MB, maximum of 1 byte, comma, the minimum would be 32 MB here, and this would be 32 MB. So what did I change here is the maximum split size. So we have to set for this particular case the maximum split size as 32 MB. MapRed dot max dot split dot size is equal to 32 MB. So if you will have to change this value, right, to 32 MB, and then you will get your input split size as 32 MB. For the third case, what should the values? My left hand side is, so my left hand side is 120 MB, which is equal to, the formula is maximum of minimum split size, comma, minimum of maximum split size, comma, your block size, the block size remains the same, which is 64 MB. So maximum of, what should I keep it? It should be one. I'll change the minimum split size this time, 120 MB, comma, minimum of the maximum split size. I can make the default value of 2 raised to 63, comma, 64 MB. So this would be maximum of 120 MB, comma, the minimum would be 64 here, and the maximum would be 128. So in this scenario, if I want my left hand side, that is the input split size, as 64 MB, then I'm gonna change my minimum split size. MapRed dot min dot split dot size. That's a property. So by changing the minimum and the maximum, you can get the desired input split size, and you can change the number of map tasks. These things we're gonna see in action once my AWS account is again enabled. I don't know, for some reasons I'm not able to log into my AWS account, so I cannot show this all these things in action. So once it is back, I can show you all these things, whatever we have learned today, in action, everything in action. I will start with the default nature of the MapReduce job, then I can change the input split size, and I will show you all these 3 scenarios in action.
So,
Yeah.
uh, so what is the topic that we covered? Did you cover MapReduce full, the daemons and all that?
Which one?
Did we cover all the daemons of this MapReduce processing
Yeah.
framework?
No, we are talking about the MapReduce job right now.
Okay, MapReduce. Okay,
Only MapReduce job.
okay. Yep.
Okay. Now let us see how to understand, or how to think in terms of key value pair. Or I would say that if you really want to solve a MapReduce job, I'm not going to go into very technical, but at a high level, if anyone wants to analyze the MapReduce job, how should they think in terms of a key value pair to solve the MapReduce job, or how should they think in terms of MapReduce programming paradigm? Okay. Now, before that, let us understand that whether we have really solved the MapReduce job in our previous um, experiences or not. So let us say that I give you a very simple statement of this, that I'll give you a file, and what I ask you to is to count the number of words which start with a vowel, which basically means that the output should be all the words that are starting with vowels, your A, E, I, O, U, So these are your vowels. So I want you to see, I want you to get all the words which are starting with vowels and how many times they have appeared. That's what I want to do. If you don't have any, let's say, computer science background, and you don't know any technology, you don't know anything. In fact, you consider yourself as a third standard uh, student, and I give you this statement. So what will you do? How do you count it? So you will take these steps, and please understand these steps are the exact steps which you will do it, which you will perform, or which they actually the MapReduce job works like this. Whatever the steps you perform, it's a very logical. What you do, you take a single line at a time. And I believe, why do you take a single line at a time? Because you cannot read multiple lines. You first take a single line. Yes, you take a single line. Then you start reading the words. Okay, hi, how are you? And if the word is starting with a vowel, then you take up the word and write one to it. So a third standard student, what he will do, if given this problem, he will ignore hi, he will ignore comma, he will ignore how, but he will take up r because it's a word to start the vowel, and then he put r1 on his notebook. Okay, if the word is already existing, then you will add just word one to it. Okay, okay, then he goes to the next line, and then again he writes I1, am1. How are you doing? Again he got the R, and R is in his notebook. Then he will write 1 comma 1, right? Then he will write apple 1, is 1, orange 1. Then again orange has appeared, orange again orange 1 1, is has again appeared 1 comma 1, apple has again appeared 1 comma 1. How you are finding? Again R came up, so R 1 comma 1, finding the weather. I hope you will do this, right? Yes or no? And then you will add all the ones. 3, 1, 1, 2, 2, whatever, 1. So R has appeared 3 times, I has appeared 1 time, am has appeared 1 time, apple has appeared 2 times, and so on and so forth. You will do this actually. And this is exactly the same way, but a third standard student is doing it for us, right? So what you have done exactly is you are mapping phase where you are counting and producing 111, and a reduce phase where you are adding it up and giving at the final output. Now let us talk about what is mapper. So a mapper is the first phase of the MapReduce job. So we have already seen in our starting of the session that a MapReduce job always starts with the map task and ends with 0 or more reduced tasks. Also, we have seen the design principle. The second point is a MapReduce job. In a MapReduce job, the reduced task will never ever start until as all the map tasks are finished. Now, here mapper is the first phase of MapReduce job. We know now, and it works typically on one block of data. The word typically, I believe now it's clear to everyone that the word typically means that you have the flexibility to change the amount of data that each map task is going to process, and that's what we have covered right now. The last topic of input split size. A MapReduce framework always try to ensure that a map task run closer to data to avoid transfer of data or to achieve data localization. So data localization concept, again I want to reiterate, the data localization concept is applicable only for the map task, not for the reducer task. Now the very first thing about the entire MapReduce job, you need to understand it works only on key value pair. So regarding the key value pair or regarding the word key, I believe you have all this while from in all your experiences, you might have encountered a lot of keys. Let me enumerate for you here. You have heard of primary key, you have heard of secondary key, you have heard of foreign key, surrogate key, byte keys, home keys, lot of keys you have encountered. To understand the MapReduce job, you need to flush out the meaning, or you need to flush out everything. You should not attach any meaning to the key. You should not attach, you should not say it's a duplicate key, you should not say it's a unique key, it's a primary key. No, should not attach any meaning to the key. That's the first thing. Okay, and the key is always assert the value. Great. So that's the first thing, a little bit of understanding of our mapper. So it's better we will start tomorrow. It's already been late. So what we will do, we'll start from here and we'll continue our understanding of mapper and reducer tasks from tomorrow. Our next class, we'll talk about this.